This is part B of the video on data representation, looking at number-based conversion. So in the first part, we went through, first of all, what is denary? How can you convert between the binary and denary number bases? And then we looked at converting from denary to binary. And then we finished up looking at hexadecimal, which is base 16, and how to convert a hexadecimal number into a denary number. So some of the things I'm just going to expand on this to kind of look at that extra criterion about why we use hexadecimal. So we're going to move on to this in more detail in a second. But if I have a very long binary number, such as like this, if I were to write a denary number of a similar length, it would simply look something like this. So obviously this is more kind of advantageous, and this is because it's a lot shorter. So therefore it saves screen space, easier to remember, easier to input for the user, etc. So you quite often get a question on the benefits of using hexadecimal over denary. Some common misconceptions are things like takes up less space on the computer. This is not true. It's the exact same form of data. It's just a different way of expressing it. So please don't write anything along those lines. All right, so now we're now going to move on to the other way around. So converting a denary number to hexadecimal. I'm going to go for some kind of harder ones, I think, with this. So we're going to have a look at converting the denary number 216. Okay, so the way to work this out is to think how many 16s fit into n, so where n is your number, and this becomes your left column, and then what's left over. When I mean that, I just mean the remainder, and this becomes your right column. Okay, so it's really worth kind of having some way of working out your 16 times table. And the way I do this is just, we know 1 times 16, we know 2 times 16, and you can know, as long as you remember 5 times 16 and we know 10 times 16, then you have a kind of good reference point to work this out, especially if you're someone like me who hasn't done long division for a very long time. So if we think about how many 16s fit into 216, so I know that 20 times 16 is 320, so we don't have to go that far. So let's try 15 times 16. So if I add together 10 16s and 5 16s, I get 240. Okay, so we're getting somewhere. So I know that 2 16s are 32. So let's have a look at taking away 32 from 240, and what that gives us is 208. Okay, so then we're getting there. So 240 is 15 16s, and then 2 16s is 32. So what we actually got there was 13 times 16. Okay, so 208 is 13 16. So this means that 13 16s fit into 216. So our left-hand column is 13, and the remainder is, so let me make this a bit more clear. So what we're doing is 216 divided by 16. And what this gives us is 13 with 8 left over. So as I said at the start, the number of 16s that fit into your number becomes your left-hand column, and this is 13. So do you remember what 13 is? So A is 10, B is 11, C is 12, D is 13. So this means we get a D in the left-hand column, and our remainder, which is 8, becomes the right-hand column. So what this means is the denary number 216, when converted into hexadecimal, is D8. So let's have a look at doing one more example, because this is pretty tricky. So let's have a look at doing another denary number. So this time we're going to do 144. So again, it's just the same process, and all you're thinking about is how many 16s fit into n. This time n is 144. So what I know here is that 10 times 16 is 160. And if I take away 16 from that, what I actually get is 144. Okay, so 9/16 is 144. So this means 9 remainder 0. So the hexadecimal number that this will give us is exactly that, 90. So what this means is 144 in denary is 90 in hexadecimal. And it's worth noting here, so you may get this in your exam and it may throw you off, not all hex numbers use the letters. Please don't get confused. Okay, we're now going to move on to hexadecimal and binary, and this is actually really easy. All you have to remember is 4 binary bits, so a nibble from the last video that we looked at. 4 binary bits equals 1 hex digit. So if I have a binary number such as this, all I need to do is split it up into 2 sections. So split the byte up into 2 nibbles, and then I just need to calculate what each nibble is. So I know that this is 1, 2, no 4s, and an 8. So this number is 11 in denary. And this number is 1, 2, 4, and 8. So this is 15 in denary. And then all I have to do is convert each one to a hex number. So 11 is B and 15 is F. So this means that the binary number 10111111 in binary is BF in hexadecimal. And it's the same the other way around. So you might get, they generally don't go over a byte's worth. So maximum number is 255. But if you, oops, we've just done the wrong one. I've just shown you binary to hexadecimal. So now let me show you the other way. So what we're doing now, in fact, let me just change this. So we started with binary to hexadecimal, and in a second, I'm going to show you hexadecimal to binary. Again, it's really easy. So each hex digit is just worth 4 bits. So you won't get this in the exam, but if for example, if we had a big hexadecimal number like F7A2, all I have to do is convert each digit, so F, then 7, then A, then 2, into 4 bits. Okay, so F is 15 in binary, this is 1111. 7 in binary, so you standardize each one to 4 bits, and what this means is if you need a 0 at the start, you have to put the 0 there. A is 10, so that would be 1010, and 2 is 2, so 0010. Okay. So what this means is F7A2 in hex is 11111110100010 in binary. Okay, it's really simple to do this, but you're lucky because in the exam you're only ever going to get 2 hexadecimal digits or a byte's worth of binary, so 8 bits of binary. So in this video we finished off looking at teaching you the skill to be able to convert between the 3 different number bases, so denary, base 10, binary, base 2, and hexadecimal, which is base 16.